Greetings everybody. On this video we're going to explain how to find coexisting attractors in continuous chaotic systems. And for that I'm using a system taken from this publication which is called Chaos Synchronization, Anti-Synchronization and Parameter Estimation in a Chaotic System with Coexisting Hidden Attractors. The topic of that paper was basically observer design. We're not gonna bother with that part of the paper. I'm only going to focus on the system that we had. Okay, so this is the system that we considered in that paper. It has four parameters: A, B, C, D, and K, so five parameters. Okay, and by trying out different initial conditions for fixed parameter values, okay, as you see right here, we found out that the system had coexisting attractors as we changed the initial condition of x3 0. Okay, so the system has four states, it's four-dimensional. We have fixed the parameters a equal 4, b and c equal 1, k equal 12, d equal 4. And each time we changed the initial conditions, we basically kept x1 0, x2 0, and x4 0 equal to 1. But x3 0, we changed it each time. Okay, I can give you a very simple simulation here in MATLAB. Okay, basically I'm changing the initial condition each time. Let me change the size as well. And you see that the third initial condition each time is random. Okay, so let's simulate the system again and again. And you see, let me run many different simulations for random initial conditions. And you see that sometimes the attractor ends up in a different place. Okay, you see that some attractors happen to fall one above the other, but you see right here we have many different positions. And you see, let me make this higher, that although from the four states, three of them pretty much remain in the same range, x3, as you see right here, okay, x3 changes. So the attractor in the dimension of x3 can move up and down, okay? And this all happens for fixed parameter values, okay? We only change the initial conditions. So this means that this system has coexisting attractors. You can see them right here, that they lie in different positions in the state space. So my question is this: how can we find out how many different coexisting attractors we have? As you saw right here, I did a simulation for random initial conditions and I used hold on. So I managed to understand and be absolutely sure that we have coexisting attractors. But is there a way to actually somehow plot them all together to get a good understanding of how many they are? And yes, there is a way, and the way for doing this is basically to have a bifurcation diagram, pretty much like I showed you in previous videos. You can find in my channel and in the playlist that I have in the description of the video. Okay, but here instead of choosing a bifurcation parameter, one of the parameters of the system, we're going to choose as a bifurcation parameter the initial condition x30. Okay, so I have this code right here. Let me explain it. All right, just follow my mouse to understand the code. I begin by initializing the parameters of the system, A, B, C, K, D, and X0, which I'm gonna change later though. Okay. I choose some simulation parameters. For example, I simulate the system for a lot of time, for the 4,500 seconds. Okay. I choose as a transient 500 seconds, and I choose as a step size 0.01. Okay. I choose my index of choice, I'm going to explain later, which is the third state, and this is because we found coexisting attractors with respect to moving around in the third state of the system, x3, as you see right here. Very nice. I choose the ODE solver parameters with a relative tolerance of 10 to the minus 4. Okay, this is optional. And then I choose the parameter range of interest. For example, here I want to find out how many coexisting attractors we have when the third state, this one, changes from 0 to 5. Okay, so I choose from 0 to 5. You can choose another range in your own system. Okay, I choose a relatively small interval step because I want to get a very detailed diagram. This is a pre-saved matrix where I'm gonna save the local maxima of the system. Okay. This is just for so that the simulation runs a bit faster. And then I have a dummy variable. And let's go to the main code. I go inside a for loop where the initial value goes into the step interval, which basically is from 0 to 5. And at the start of each simulation, I set the x0 equal to 1, 1, and the initial condition of x3 will change in each time. Okay, so basically x1 0, x2 0, and x4 0 remain at 1. Okay, and x3 0 will change each time going from 0 up to 5. Okay, as a value. Then I simulate the system for this initial condition which changes each time. The other parameters a, b, c, k, and d remain the same. I discard the transient behavior. I save the rest of the state in a separate vector. Okay. And then each time I find the peaks of the solution for the third state. Okay. So each time what I do is this. I simulate the system, discard the transient, find out the local maxima for the third state, which is the state of interest, and these local maxima are saved in a vector M, not a vector, sorry, a matrix M. This is the matrix that I have pre-saved with none with okay, blank values. Okay, so I save the local maxima for the third state, which is the state of interest that we saw goes up and down. Okay, and once the for loop finishes, okay, I don't use that. This is commented out. I simply plot all of these different local maxima for the third state for the different initial conditions. Okay. And the diagram I get, it takes around an hour to plot, depending on how fast your computer is. Okay, is this one. Okay, come on, let's zoom in. So basically, what is this diagram? It depicts, okay, what are the values of the local maxima of the solution for x3, for the third state, when we simulate the system from different initial condition x30. Okay, so I choose a different initial condition that goes from 0 to 5 for the third state. The other initial conditions for x1, x2, and x4, they are fixed. The parameter values of the system are fixed. Okay, only this initial condition changes. And we observe that each time we simulate the system, okay, the local maxima for the solution in the third state move around. So you see, for most parameter values, the local maxima are around 0, but for some initial conditions, they move around. For example, here they move to minus 40, minus 45, minus 50, minus 60 up to 1, minus 100, and minus 120. Okay. So this moving around of the local maxima indicates that the system has coexisting attractors when we are changing the initial conditions. Okay, so the change in the local maxima is basically, I'm sorry, this change that we saw right here in the phase diagrams. Okay, this is what this diagram represents. All of the different possible coexisting attractors that you see right here with the local maxima changing each time. Let me run a couple more. Okay, all of this change in the x3 direction is depicted basically by the changes in the local maximum. And for me, this is the best way of giving a very clear depiction of how many coexisting attractors we have. Basically, here we have far too many. It's even difficult to measure them because we have these small ones. We have the big line right here and the big line right here, but then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I mean, it has possibly could be 50, 60 different coexisting attractors here. Okay, so this is a very, very interesting behavior. And basically what is this called in the literature is a bifurcation diagram with respect to initial conditions. And for me, it's the best way to depict how many coexisting attractors we have in the system. Okay. Now, the basic question is this. How do we choose which initial condition we are going to change? Okay, there is no clear way to understand which is the initial condition that gives coexisting attractors. It may not just be one. The system may have coexisting attractors with respect to many different initial conditions. Okay, so basically, you need to have some tryouts to find out if the system has coexisting attractors. As you saw me here, for example, running the system for random initial conditions, you basically have to do the same to find out, first of all, if the system has coexisting attractors, and secondly, for which initial conditions the coexisting attractors appear. Okay, it may be one, but it may be more than one initial conditions that give coexisting attractors. So a little bit of trial and error is involved, but after you find out and choose your correct initial conditions, then the diagram is very, very analytical in depicting how many coexisting attractors we have. Okay. I'm going to put a link into the description of the video for this MATLAB code, and you only need to change the parameter inside the for loop, as you see right here. Okay, whatever parameter the original code has, you just replace it with your own parameter for changing the initial conditions. Okay, any questions that you have, please write them down in the comments, and I'll see you in the next video.